My dear students, today we shall start the design of tension member. First of all, I want to show you a flow chart of design of tension member that you can understand the method. Keep in mind that the tension member design depends upon three types of failure. One is cross section yielding, that is niche section rupture, and that is block shear failure. So the first step is you have to select the actual cross section of the member. And how to do it? You can approximately calculate the cross section using this formula TDG is equal to AGFY by gamma m0. Or you can approximately calculate the niche section by this formula, and after that by adding 20% or 25% with AN you can get the cross section. Now we are going to use this formula TDG and this formula TDN to calculate the cross section. In this flowchart you can see that we can calculate the cross section AG1 from cross section yielding and calculate AN, and after that by adding 10 to 25% with it you can get the cross section, that is AG2. And after that compare this AG1 with AG2. The greater value between AG1 and AG2 will be considered. Now if AG1 is greater than AG2, then AG1 will be considered. Otherwise if AG2 is greater than AG1, then AG2 will be considered. Now open your handbook and select a providing cross-sectional area which is approximately same with your calculated AG. After that you calculate the bolt strength from shearing strength and bearing strength. If shear strength is greater, then bearing strength will be the strength of bolt, or if bearing strength is greater than shearing strength, then shear strength will be the strength of bolt. Then you have to calculate number of bolt, and please keep in mind this portion you can do at the beginning. That means here you can perform this task. After that you can go for calculating approximate AG. Now the next step is you have the provided actual cross-sectional area from handbook, and this cross-sectional area obviously not equal to your calculated cross-sectional area. That's why the design strength of this connection will be changed. Now from those three TDG, TDN and TDB, that means cross-section yielding, niche section rupture and block shear failure, you have to calculate the actual design strength of this member connection, and after that you have to check whether this design strength is greater than applied load or less than. If it is greater than applied load, then it's okay. Then go for slenderness ratio check. If it is okay, then your design is complete and go for drawing. And if the design strength of that selected cross-sectional area is less than applied force, then you have to go for redesign. That means you have to choose another cross-sectional area which is greater than the previous one. So this is the fundamental procedure. You can follow this procedure, and obviously when the shape of the cross-section will change, then some modification of this chart is also required. So this is a basic or fundamental method that you can follow. Now we can go for design. The problem is a tension member 0.95 meter long and is to resist service dead load of 20 kN and a service light load of 60 kN. Design a rectangular bar of standard structural steel of grade Fe410. Assume that the member is connected by one line of 16 mm bolt of grade 4.6. Now for Fe410 grade of steel, Fy is equal to 50 MPa and Fu is equal to 410 MPa. The partial safety factor for material against yielding gamma m0 is equal to 1.1 from table 5 of IS 800. You can see the table 5 for partial safety factor for materials, and the resistance governing by yielding gamma m0 is equal to 1.1. And partial safety factor against ultimate stress gamma m1 is equal to 1.25. So gamma m1 is equal to 1.25. You can see. And partial safety factor for material of bolts gamma mb is equal to also 1.25. This is gamma mb partial safety factor for bolt, bearing type bolt. The partial safety factor is 1.25. Partial safety factor for dead load and live load, this is 1.5. This is table 4 for partial safety factor for load. And you can see dead load plus live load plus crane load. You can apply the 1.5 partial safety factor for dead load and 1.5 for live load for limit state of strength. So the partial safety factor we have to apply, that is 1.5. Diameter of bolt is equal to 16 mm. So diameter of hole is equal to 16 plus 2 is equal to 18 mm. You can see table 19 of IS 800. This is table 19, and from 16 to 22 we have to add 3 mm to calculate dia of hole. So design factor load is equal to 1.5 multiplied by dead load plus 1.5 multiplied by live load, total 120 kN. The required neat area on the basis of neat section equals TDN is equal to 0.9 AN FU by gamma m1, and N is equal to, you can calculate 406.5 mm square. And this is neat area, that's why we are adding approximately 25% of the neat area with it to convert into the gross area. So gross area will be 508.12 mm square. And gross area we can calculate from gross section yielding also. From this equation, gross area is equal to 528 mm square. Now the greater value of these two values will be taken. So our first trial area is equal to 528 mm square. If the 10 mm thickness is provided, then width of the bar will be 52.8, approximately 60 mm. Now we have to provide the bolts in one line. So in the question it is given, assume that the member is connected by one line of 16 mm dia bolt. So the neat area will be B minus NDH into T. So B is our 60 and N is equal to number of bolt, that is 1, and DH is equal to 18, and T's thickness is 10 mm. So 420 mm square is the neat area, which is also greater than our calculated neat area, that is 406.5 mm. Hence, after selecting this plate, the member will be in safe condition. The failure of bolt that you need to calculate, and it is governed by shear failure and bearing failure. Now calculate the strength of the bolt, which will be the minimum of shear strength and bearing strength. So you need to calculate both strengths, shearing strength and bearing strength, both. So neat tensile stress area of 16 mm diameter bolt is 0.78 into diameter of bolt is equal to 157 mm square. The strength of the one bolt in single shear equal FUB by root 3 gamma mb AN B into NN. This formula is provided in clause 10.3.3 IS 800. This is clause 10.3.3, and you can see V DSB is equal to VNSB by gamma mb. So V DSB is equal to nothing but FUB by root 3 gamma mb into NN ANB plus NS ASB, and assume that there is no ASB. What is ASB? Is the nominal plane shank area of the bolt. So we don't have that type of shank, so we are neglecting this part. We are considering only A and B. So the strength of one bolt you can calculate, that is 29 kilonewton. Now the strength of one bolt in bearing equals 2.5 kVdt Fu by gamma mb. You can see in clause 10.3.4, this is clause 10.3.4 for bearing capacity of the bolt, and you can see V dpp is equal to 2.5 kVdt Fu by gamma mb, and kb is the smaller of all those parameters. Now we don't have end distance or pitch distance, so we need to assume that parameter. Let us assume edge distance E for rolled edge. The minimum edge distance we are considering, that is 27 millimeter. Clause 10.2.4.2 is providing this limitation of minimum edge distance. This is clause 10.2.4.2, and you can see 1.5 times of the hole diameter in case of rolled, machine frame cut, sawn and planed edge. So we are assuming that this is rolled edge, that's why we are multiplying by 1.5. For rolled edge we are multiplying 1.5. Now assuming that pitch distance P is equal to minimum pitch distance 16 into 2.5 is 40 millimeter, and clause 10.2.2 is providing this limitation. This is clause 10.2.2 for minimum spacing. The distance between center of fastener shall not be less than 2.5 times of nominal diameter of the fastener. So we are considering the minimum pitch distance, that is bolt diameter multiplied by 2.5, that is 40 millimeter. Now one thing you please keep in mind, that you don't need to apply only the minimum edge distance or minimum pitch distance. You can apply the edge distance greater than 27, and there is a limitation of maximum edge distance obviously, and maximum pitch distance we will discuss later. But suppose you are providing here 30 millimeter or 40 millimeter, you can do it, because your providing edge distance or pitch distance is greater than the minimum limitation. So now KB we have to calculate, and from all those parameters the minimum value will be taken, that is 0.49. so KB is equal to 0.49. Now the bearing strength of bolt is equal to 64.28 kilonewton. The strength of the bolt will be minimum of strength in shearing and bearing, that is 29 kilonewton. The shearing strength of bolt is 29 kilonewton. This is 29 kilonewton, and bearing strength is 64.8 kilonewton. The minimum of those two is the actual minimum strength of bolt, that is 29 kilonewton. So to resist the 120 kilonewton load, the required number of bolt will be 4.14, and the actual number of bolt will be 5. So let us provide bolt in one line at a pitch 40 millimeter, end distance 35 millimeter. I am not providing the minimum edge distance here. The minimum edge distance is 27 in IS 800 plus 10.2.4.2. you can see. Now I am providing the greater one, and edge distance is 27 millimeter. Now we have to check the block shear strength. Now you can see that this is the plate, and bolt is placed in one line, and number of bolt is 5. And when this member will be subjected to a tension force, the block shear failure can happen for this connection like that. You can see the lower part of this member can be teared out from the main connection like this way. Now to calculate the block shear strength, you need to consider this part, and you have to calculate the neat area of this surface and gross area of this surface, and neat area at this surface and gross area at this surface. So the gross area will be this blue surface, that means 195 into 10, and the neat area will be 1950 minus 4 into 18 into 10 and 1 for the end bolt, that is 9 into 10, and ATG is equal to 27 into 10 and ATN is equal to 27 into 10 minus diameter of hole. So TDB1 and TDB2 you can calculate, that is 309 and 225.65. So block shear failure will be minimum of those two, that is 255.65 kilonewton, and 255.65 block shear strength is also greater than the applied load. So this connection is safe against block shear failure. Now check the slenderness ratio. The slenderness ratio is L by R, and R is the radius of gyration. The formula is root over I by A. I is moment of inertia, A is the area. So moment of inertia is equal to B into T cube by 12 and area is equal to B into T. So actually T by root over 12. So radius of gyration is 2.88 millimeter and length of the bar is 0.95 meter is given in the question. So slenderness ratio is 929.68, which is greater than 400. You can see in the table 3 of IS 800. This is table 3 for maximum value of effective slenderness ratio, and you can see member always under tension, the maximum slenderness ratio should be 400. So this is under the limitation, that means it's okay. So now the design is completed. In our next video we shall go for another design of a truss. Thank you.